In this video, I'm going to be talking about free body diagrams, what they are, what their purpose is, and give you a full understanding of how they work. If you want to watch a shorter and more condensed overview video, which I do not recommend unless you already have an understanding of how they work, you can click on link number 1 in the description. Otherwise, if you're learning this for the first time, I highly recommend you watch this entire video. A free body diagram is basically a drawing of a box with arrows sticking out of it, where the box represents an object, any object, and the arrows represent all the forces applied to that object at the same time. And then the strength of those forces are written next to the arrows, and then the directions of the arrows, the forces, are clearly shown so that we know how strong the forces are and what directions they're heading, so that we can do mathematical calculations afterwards. So you can sort of get a visual representation of what's going on in a situation when it comes to forces. So maybe you have an object with, let's say, 30 pounds of force because of gravity. Then let's say a man is pulling the object with 50 pounds of force and the rope is pulling in this direction. And then let's say we have 10 pounds of force acting in the backwards direction because of friction opposing the man pulling the object. And since the object is exerting 30 pounds of force down onto the floor is then going to exert 30 pounds back up onto the object, which is called the normal force. Then this would be pretty much generally an example of what we would call a free body diagram. Keep in mind that each free body diagram is going to be unique because each situation is different. So sometimes a free body diagram can be drawn a little bit differently. Some variations of it may look like this, but at the end of the day, it's all pretty much the same thing. So in order for something to be a true free body diagram, it must include two things. One is how strong the forces are, and two, what direction those forces are acting. And they'll typically look something like this. So as you can see by the free body diagram, the strength of the forces are represented in pounds of force in this case, and the directions of the forces are represented by the directions of the arrows, up, down, left, or right. Sometimes a force will be not perfectly in a cardinal direction, up, down, left, right. Sometimes it'll act at an angle like this force here. I'll get to that later in the video. So in this case, the forces, the arrows, which are called vectors, are labeled in pounds, as in pounds of force, not pounds of mass, but pounds of force. If you want to see the difference between pounds of force and pounds of mass, you can click on link number 2 in the description. However, the pound is not the only unit of force. You can also have forces that are measured in something called newtons, which is represented by just the letter N. If you don't know what a newton is, you can click on link number 3 in the description. Another unit of measure for forces would be something called Kips, which Kips actually stands for kilopounds. So just like 1 kilogram is 1,000 grams, a kilopound, aka a kip, is 1,000 pounds. So for example, 18,000 pounds of force would be 18 kips. So your free body diagram can be labeled by any units of force, but all the units must be units of force, and you want to make sure that all the units are the same. So like you don't want to have newtons and pounds on the same free body diagram, just like you can't compare, well you can, but you don't want to have something that is measured in inches and meters on the same chart or whatever. So make sure that like newtons and pounds shouldn't be on the same body diagram. They should all be consistently newtons, or all pounds, or all kips, or all the same type of unit. And all the units should be units of forces because only forces get put onto free body diagrams. So let's say you know what the temperature is, or you know what the air pressure is. Those things might be useful pieces of information for something else, but when it comes to free body diagrams, they do not belong. Only forces go on a free body diagram. Then when you finish drawing the free body diagram, you can use it as a visual representation to get what's called a resultant force or a net force, The best way I can describe that would be to imagine that you're shopping in a store and you have some coupons. When you go to the cash register, you would add up all your items and subtract all your coupons to get a net total or a resultant price, which is how much you pay the cashier in the end. So here, we take the summation, which is the sum of all the items minus all the coupons. So let's write this out like a mathematical equation. So I'll write the summation, this symbol here, the sigma, it's a Greek letter, sigma, which means the sum or the total of everything we have. So we want to know how much money to give the cashier. So we would do this, plus $10, plus $20, plus $50, minus $40, minus because it's a coupon, and then minus the $5 coupon. When it's all said and done, the $35 is what I actually pay the cashier. So the $35 would what we would call the net cost or the resultant cost. Also, it's worth noting that the order in which the items that are listed on the receipt don't matter, as long as you add all the items and subtract all the coupons. If I mixed up the order in which things were listed, the total cost or the net cost would still be $35. Also, it wouldn't matter if I put minus signs at the items and plus signs at the coupons, and then the total would come out to be negative $35. As long as the cost of the item goes against the grain to the coupons and you subtract the differences, the final price will come out the same. It'll just be negative. So what does all this have to do with free body diagrams? Well, just like how we added all the items and then subtracted all the coupons to get a resultant price or net price that we paid the cashier, the same thing happens in free body diagrams, except instead of adding and subtracting dollars, we're adding and subtracting forces. And instead of figuring out a net price that we owe the cashier, we need to figure out a net force. So imagine a game of tug of war. If the guy on the left is pulling the rope with 80 pounds of force, and the guy on the right is pulling with 100 pounds of force in the opposite direction, we know that the guy on the right is going to win the game because he's pulling harder, and we know he is going to win by 20 pounds. So how did we know that? Well, just like we added up all the products and subtracted all the coupons to get the final price to pay the cashier, you do the same thing with forces. Same thing here. You take the summation of the net forces in the x direction, left to right, left and right, to get the net force. And we have a plus, positive 100 pounds going this way to the right. And then we say minus 80 pounds, since it's going in the opposite direction, it's going this way. So the 80 pounds is going against the grain to the 100 pounds. The two guys are pulling in opposite directions. So 100 minus 80 equals 20. So the final result is going to be 20 pounds of force. So since it's 20 pounds in his favor, the net force is 20 pounds going in this direction. So here's the exact same scenario. It's the same situation, same everything, except it is drawn as a free body diagram. Here's the 100 pounds of force from the guy pulling to the right, and here's the 80 pounds of force of the guy pulling to the left. So we know that the net force, or the resultant force, is 20 in this direction. So F net x, meaning the net force in the x direction, equals 20 pounds. So 20 pounds of force in this direction. And then similarly to how we add and subtract all the items and coupons on the receipt, the order in which you add and subtract the forces on a free body diagram don't matter either. As long as the opposite facing forces get the opposite mathematical operations from each other, it doesn't matter. So like if you have a force going in opposite directions, you can't add the forces together. You have to sort of subtract the difference because they're opposing forces. Another thing that doesn't matter when it comes to free body diagrams is which side of the box the arrow is on. So for example, a 30-pound force pushing the box to the right is the same thing as a 30-pound force pulling the box to the right, because the force is still 30 pounds and the direction is still going to the right. Something else that's worth mentioning is that the way the arrow is pointing is called the direction of the force, and how strong the force is, meaning how many pounds it is called the magnitude. So here, the magnitude is 30 pounds of force, and the direction is to the right. Here's another example where the guy on the left is pulling 80 pounds, and the guy on the right is pulling 75 pounds. The free body diagram would look like this. Same scenario, 80 pounds and 75 pounds. And we would say the summation of the forces in the x direction, again, this is left to right, positive 75 pounds minus 80 pounds, because the forces are going against the grain to each other in the opposite direction. So we take 75 minus 80, comes out to be negative 5 pounds of force. But in all seriousness, like I was saying before, you don't really have to worry about whether or not it's positive or negative. This is because a negative force in one direction is the same thing as a positive force in the opposite direction. So for example, negative 18 newtons of force in this direction is the same thing as positive 18 newtons in the other direction. So for the example we're working on, when it comes to the resultant force coming out to be negative 5 pounds of force, you don't really have to worry about whether it's positive or negative. Just understand that the net force, or the resultant force, is 5 pounds, and it is going in this direction. Here's another example. Here you have someone pulling 80 pounds of force to the left, and on the other side you have one person pulling 100 pounds of force and another person pulling 75 pounds of force. This is what the free body diagram would look like here. Notice how you have more than one forces acting together on one side. So to find the resultant force, you take the summation of the forces, the net force in the x direction, plus 100 pounds, plus 75 pounds, and then minus because it's in the opposite direction, minus 80 pounds to get a resultant force, or net force, of 95 pounds going in this direction. And then the same thing applies to forces when acting vertically, meaning up and down, which is the y-axis. Also in this case, I'm dealing with newtons instead of pounds. Again, newtons, pounds, kips. There's probably some other ones that I don't really know about that aren't talked about a lot. So here we have forces going up and down. So again, we take the summation of the forces, but this time we'll say summation of the net force in the y direction, which is positive 35 newtons plus 20 newtons minus because it's going oppositely, minus 40 newtons. And then the resultant force, or the net force, equals 15 newtons in the upward direction. So what would happen if we had an example like this? Determine how much force X needs to be in order for the net force to equal 0. So in other words, what does X need to be in order for the situation to cancel out? What this is basically saying is, what does X need to be for the tug of war game to end in a tie? So like always, we would do what we've been doing, take the summation of the forces, the net force, in the x direction, just like we've been doing. So we take negative 10 pounds plus 8 pounds plus x, and then the whole thing equals 0 pounds, like it says in the directions. It asks for x when the net force is equal to 0. So x equals 2 pounds. So in order for the box not to move, x would have to be 2 pounds of force in this direction in order to make this scenario be at a standstill. So by now you should have a pretty good idea of what free body diagrams are and what their purpose is. They're basically just there to show you the final result when a bunch of forces are acting on an object at once. One thing you'll definitely encounter at some point would be a force acting in a diagonal direction. I mentioned this a little bit in the beginning of the video. If you look at the direction of the force, it's actually not acting in any of the cardinal directions, which is up, down, left, right. The direction of this force is actually acting in two cardinal directions simultaneously. So in other words, the diagonal force, the arrow, the solid arrow, is acting upward and it's acting to the right at the same time. Let me show you what I mean. Imagine two guys are given the task to slide a box diagonally across the floor. And we're observing these two guys from up above. So the two guys are trying to slide the box and we are directly above them watching them. So let's say the names of the guys are person X and person Y. The goal is for the two guys to move the box diagonally in this direction. So if person X moves the box in the X direction and person Y moves the box in the Y direction, they will both work together at the same time and they will both together move the box diagonally. So person X does his fair share of moving the box in the positive X direction, and person Y does his fair share moving the box in the positive Y direction. So here's the same scenario, except it is drawn like you would see on a free body diagram. The vector, which is the arrow, the solid line arrow, not the dotted lines, but the solid line arrow, the vector. The vector represents the box moving diagonally. The two vectors shown as dotted lines are represented as each of the two guys. So this dotted line represents person X doing his fair share, pushing his box to the right, and this dotted line represents person Y doing his fair share, pushing the box forward. So this process is referred to as breaking down a diagonal force into its individual components. We're taking a diagonal force and breaking it down into its individual X and Y components. So what would happen if one person pushes harder than the other? What if person Y pushes harder than person X? If person Y pushes harder than person X, the box will still move somewhat diagonally, but it will be more in favor of person Y because person Y is pushing harder than person X. Same thing, if person X pushes harder, the box will go more favorable in the X direction. So for this example, the solid arrow is what I call the main force, which is the force itself. Maybe it's a person pulling the box with a rope at a 50-degree angle from parallel to the surface. That is the actual force. And the vectors with dotted lines are the individual components of the force. They are the X and Y portions that make up the main force. So now you might be asking yourself, why are we doing this? Why are we taking the diagonal forces and breaking it down into its X and Y components? The reason is so that we can use those individual X and Y components to find the net force in the X direction. Remember, like what we were doing? It has to be in the X and Y direction, otherwise you can't compare it. So we're going to use the components to find the net force in the X direction. So summation force net in the X direction. And then we can find the forces in the Y direction, summation F net in the Y direction. And therefore, we can just ignore the main force. We didn't get rid of the main force. We just took the main force and broke it down into its individual up, down, left, right components. So that if there were more forces, we can apply the tug of war game analogy going left to right, which is the X direction, and we could have the tug of war game going up and down, which is the Y direction. Now, all we have to do is figure out how many pounds of force the X and Y component forces are. So in other words, how strong, or how many pounds, are those individual X and Y components we just made? What are their magnitudes? The answer to this question is actually found through trigonometry. If you don't know trigonometry or you're not familiar with it, in terms of free body diagrams, there's only a couple things you really need to know how to do. So it's not going to be a huge deal for the time being, because in this video, I am just going to cover the parts that you need to know in free body diagrams. So throughout this video, you've heard me refer to forces as vectors. A vector is basically just the name we give to those arrows. Those arrows that show what direction a force is going and how strong the force is, which is called the magnitude. The thing about vectors is that you can actually use trigonometry to solve for a vector the exact same way you would use trigonometry to solve for the sides of a polygon. So, for example, if we have a triangle like this, there's a 33-degree angle. The length of the hypotenuse, this one here, is 55 feet long. I can use basic trigonometry to figure out the lengths of side y and x. If you're not familiar with using sine and cosine to determine sides of a right triangle, I have another video explaining it, and it will be link number 4 in the description. If you want to see a similar video I made that does the same thing with actual vectors, you can click on link number 5 in the description. So to solve for x and y, I take 55 sine 33 to get 29.96 feet, which is y. And then 55 cosine 33 to get 46.13 feet, which is x. Here's the exact same thing. Same numbers, same everything. The only difference is that instead of using sides of a triangle, we are dealing with the main force accompanied by its individual x and y components. The only thing I'm going to do here is I'm going to shift the y-axis component over to the side so that it makes a triangle shape. If I shift the y component back and forth, or shift the x component up and down, it's not going to affect the outcome because up is still up, down is still down, left is still left, and right is still right. So here's what the original vector force looks like, and all I'm going to do is just shift the arrow over to the side so that it forms a triangle, and it resembles the triangle we just did. Now the triangle I made using vectors is the exact same thing as the first triangle. The numbers are the same, everything's the same. The only difference is that this triangle measures in feet and this triangle measures in pounds of force. But the numbers, the values themselves are the exact same. So basically solving for forces on a vector is the exact same thing as solving for length on a triangle. This also works with other polygons, but we're not going to get into that right now. So when it comes time to find the resultant force, since we took the main force, which is the diagonal force, and we broke it down into its individual components, and then we found the magnitude in pounds of force, we found the magnitude of those individual forces. Because we did that, now we can just ignore the main force that we were originally given, and we can fully rely on those individual components that we just made so that we can add or subtract them when we go do the summation to find the net forces. Again, we didn't get rid of the main force, we just substituted it by breaking it down into its individual components, up, down, left, right components, so that we can actually use them when we sum the forces in the x and y direction. So now we can take the summation of the forces in the x direction, lefts versus rights, and then we can do the same thing in the y direction, ups versus downs. So that is why you always need to break down your diagonal forces into their individual up, down, left, right components. So that's pretty much it in terms of understanding what to do with free body diagrams and how they're used. Next, we'll go over how to set up a free body diagram. Up until now, we've been dealing with deciphering a free body diagram. When it comes to actually setting one up, Each situation is different. Maybe you have a guy pushing objects at 70 pounds of force. Maybe it's on an incline. Each scenario is different. So there isn't any standard way of setting up a free body diagram. However, there are a couple things that almost every free body diagram has, and that is gravity and a normal force. When it comes to gravity, it seems pretty self-explanatory, and it kind of is. Gravity acts down. It always acts down. The only thing you really have to keep in mind is that forces are the only thing that go on a free body diagram. So when you're given the mass of an object, if you're given the mass of an object, when you're given the mass of an object, the mass is not a force, even if it's measured in pounds, because remember, there's pounds of mass and pounds of force. So if you're given the mass of an object, it's not a force. The only other thing you have to keep in mind is that forces are the only things that go on a free body diagram. You can also label what direction they're going, but for the most part, forces are the only thing that go on a free body diagram. So when you're given the mass of an object, the mass is not a force, even if it's measured in pounds. This is because there's actually two different types of pounds. There's pounds of mass, which is abbreviated LBM, and pounds of force, which is abbreviated LBF. So again, the mass is not a force. However, weight is a force. So like I said earlier, if you don't know the difference between pounds of mass and pounds of force, you can click on link number 6 in the description, and I'll explain it to you in simple terms. If you want to know how to turn a mass into a weight, which is a force, you can click on link number 7 in the description. It's actually not difficult. You just have to multiply it by gravity and make sure the units correspond. But if you want an explanation, which I recommend if you're not familiar, because you definitely shouldn't just memorize stuff. Don't just memorize that you multiply it by gravity. I highly recommend clicking on that link if you're not familiar. So in this example, we have an object whose mass is 15 kilograms. And since kilograms are a unit of mass, we have to multiply it by gravity, which is about 9.81 meters per second squared, which is for SI / metric units. And we get 147.15 newtons of force acting straight down. So then we label the free body diagram as such. So remember, the approximate acceleration due to gravity is about 9.81 meters per second squared if we're dealing with SI units, which come from metric units, and then 32.2 feet per second squared when it comes to American units or English units. So that's the first thing that's on almost every free body diagram. The other thing that's on almost every free body diagram is the normal force. The normal force is basically a direct consequence of gravity. What do I mean by that? Well, imagine a person sitting in a chair. Let's say the person's body weight applies 600 newtons of force down onto the chair. Because the chair is supporting the person's weight, the chair must also be exerting 600 newtons back up onto the person. Otherwise, the person would fall through the chair and onto the floor. And this concept is actually known as Newton's third law, which is for every action, there is an equal and opposite reaction, where the action is the person sitting and the reaction is the chair pushing back up onto the person for support. So the action is the weight of the person, and then the reaction of the chair pushing back up, that is the normal force, which is usually represented by the letter N on a free body diagram. So the chair pushing back up on the person, that is the reaction of the person sitting on the chair. So the 600 newtons of force that pushed back up on the person, that is the normal force. Here's another example. A person is exerting 150 pounds of weight, not 150 pounds of mass, but 150 pounds of weight, which is a force. The person is exerting 150 pounds of force onto the floor. The floor will have to exert an equal and opposite 150 pounds of force as a reaction. The 150 pounds of force is due to gravity, and the 150-pound reaction of the floor is the normal force. So going back to this example, if we have an action of 147.15 newtons due to self-weight, we must have an equal and opposite reaction because the floor is supporting the object. And because the surface creates the normal force will always act perpendicular to the surface. It will always be exactly perpendicular to the surface, even if it's on an incline. If the normal force is a reaction of the surface, and that surface just so happens to be tilted, then the normal force will also be tilted. Why? Because the surface is what actually causes the normal force. So if an object is resting on an inclined surface, the reaction due to the surface will also follow the same suit. Now, what about gravity? What direction does gravity act when dealing with an incline? Well, what causes gravity? Gravity is caused by the rotational pull of the Earth. So basically, gravity is just a phenomenon that just exists. It just exists in nature. Nature doesn't care that our object is on an incline. Gravity just does what it does, which is act straight down, always. Gravity will always act straight down, regardless of whether something is on an incline or it's flat. The only reason the normal force changes with a surface is because the normal force is already caused by the surface. Gravity just acts straight down. And it makes perfect sense too, because if you're climbing up an inclined surface, the steeper the surface, the more likely you would be to fall backwards down the slope. Or if you were looking at sliding a box down an incline, gravity is what's making the box slide down. So the normal force is just guiding it along the surface. So no matter how the surface is oriented, gravity will always act down, and the normal force will always act normal to the surface. So here's what the free body diagram would look like without the inclined surface drawn. We take the incline into account by drawing the angular difference directly onto the free body diagram. And then we solve for the individual up, down, left, right components, just like I talked about earlier, if we need to get a net force. So going back to this example, gravity is acting straight down. The normal force is acting exactly perpendicular to the surface. So in this case, the force due to gravity and the normal force just so happen to be equal and opposite in terms of magnitude and their direction, because the surface is not inclined. Perpendicular to the surface is up and gravity is down. Okay, so another thing you might need to consider is friction. Again, each free body diagram is unique, so sometimes friction does apply and sometimes it doesn't. If something is being slid across a surface or dragged across the floor or anything along those lines, friction would apply. So friction plays a role in free body diagrams just like it plays a role in real life. But how do we apply it to a free body diagram if friction is not actually a force? There will be a force due to friction, but friction itself is not a force. And remember, only forces go on a free body diagram, and each force must have a direction, right? So just like all other forces on a free body diagram, what direction does friction go? Well, the truth is there is no set direction that friction goes. It just happens. It just exists. Friction is just basically two textured surfaces rubbing against each other during motion. The question you should be asking is, what force is going to occur because of friction? Because again, friction itself is not a force. What you should be asking is, what force is going to occur because friction? So let's say that a person was pulling the object in this direction, and the free body diagram would go like this. The force due to friction will be going in this direction. Why? because friction isn't helping him. It's actually hurting him. Friction is making his job harder. So the direction of the force due to friction, not friction itself, but the force created by friction, is going to go in the opposite direction of the guy pulling. How about if the person was pushing the box? Again, when friction is introduced into this situation, the friction is making this guy's job harder. It's going against what he's doing. So the force, as a result of friction, would apply oppositely to the person pushing, because again, it's fighting him. It's going in the opposite direction that he wants it to go. Again, this force is not friction itself. This vector, this arrow, is the force that's making the guy's job harder. It just so happens to be caused by friction. And just like we do with all the other forces on a free body diagram, the next step would be to find out its magnitude. How many pounds of force is it? Well, like I said before, friction is just when two surfaces rub together. What is the actual force that is making this guy's job harder? This force, which is a force due to friction, is based on two things. The first thing is how significant the friction is, or how rough or smooth are the surfaces. The second thing has to do with how heavy the object is. The heavier the object is, the harder it's going to be to slide across the surface. And that is exactly why the equation for friction forces due to friction is mu, the Greek letter mu, times the normal force, where mu, the Greek letter mu, mu is basically a coefficient that corresponds with how rough or how smooth a surface is. It's a variable where we can just plug in a number, it's usually a decimal, that manipulates how strong the force will be, because mu is a value that takes into account how rough or smooth the surface is. And the rougher the surface is, the stronger the force due to friction is going to be. So basically, the rougher the surface is, the more difficult it's going to be to slide something across it. And mu is the coefficient, the decimal, that takes that into account. So the value of mu will depend entirely on what the object is made of and what the surface is made of. And this coefficient, mu, will either need to be given to you or you will need to look it up on a chart. You can actually find dozens of these tables online or even in some textbooks. But if you'd like to view or download the table that I'm currently using, you can click on link number 8 in the description. So if we take a look at this table, we see a list of surfaces on the left. The other two columns show you the coefficients of friction, the mu values, which, by the way, are unitless. The coefficients do not have units. So looking at the header of the table, you might notice that there are two columns of coefficients, two columns of numbers. The middle column is the coefficient of static friction, and the column on the right is the coefficient of kinetic friction. Static friction is mu sub s, mu subscript s, and the kinetic friction is mu subscript k. When you're dealing with static friction, use mu s, and when you're dealing with kinetic friction, use mu k. What's the difference between static friction and kinetic friction? The best way I can describe it would be to imagine pushing something heavy across a floor. Have you ever noticed that it actually seems harder to push an object right from the start than it does after it's moving? Well, you're actually right. It is harder to move an object when it's just sitting there. When you push an object across a surface, that jumping free sensation is because the object is experiencing static friction, but only for a split second. Actually, it's less than a second, much less than a second. But static friction only occurs during that initial sudden jolt when you move something across the floor from a standstill. After that initial jump, that breaking free of an object, the kinetic friction takes over. Kinetic friction is basically just the so-called regular friction that just occurs uniformly as the object slides across a surface. So basically, if you're sliding an object across a surface and the object is not already moving, it's at a standstill, the object will experience static friction right away and then kinetic friction for the rest of the way. This is actually a graph that shows how friction behaves over a brief period of time. So as you can see here, it starts out with that initial jolt that I was talking about, that initial breaking free. It starts out with that initial jolt of static friction here, and then it moves on to kinetic friction, where the intrusiveness or the interference of the friction becomes more constant and uniform. All you really have to do is just ask yourself what the object is doing. Is the object not moving? Does it have to be jolted forward with static friction? Or maybe the object is already moving and you don't need to be jolted free. Whatever the case is, you have to determine which coefficient you need and then multiply it by the normal force, which will give you the magnitude of the force due to friction. The force due to static friction is the static coefficient, mu sub s, times the normal force. And then similarly, the force due to kinetic friction is the kinetic coefficient, mu k, times the normal force as well. And then the direction of the force is in the opposite direction of the force being applied. Again, friction is making his job harder, so the force is not in his favor. It's going in the opposite direction because it's fighting him. So now we know how to incorporate friction into a free body diagram. We also know how to incorporate the weight of an object, and we know how to incorporate the normal force. And if a force is not perfectly in a cardinal direction, up, down, left, right, we know how to take a main diagonal force and then break it down into its individual components. And then we can get all the forces put onto the free body diagram. We know how to get the net force or the resultant force in the x direction and then get the net force in the y direction. So as I said earlier, free body diagrams are all unique to the situation that you're dealing with, but for the most part, that's pretty much all you need to know about free body diagrams. If you would like to try some practice problems with the answers given afterwards, you can click on link number 9 in the description. So that's it for this video. If you thought it was helpful, feel free to give a like or let me know what you think in the comments. Thanks for watching.